Hey guys, welcome back to Chris V's RF Designs. So in this video I'm going to show you how to find the input impedance to a double balanced mixer. So this is kind of like the next sequel of my last video where I find the input impedance of a diode using harmonic balance. So a diode is a nonlinear device, and so when you calculate also the input impedance to many other diodes here and the everything that is included in the mixer, you need to include, which are the transformers for the double balanced mixer. You can Google it and find it online, a double balanced mixer here, and that's how it would look. You'd have the center tap with the IF output right here. I put 1,000 ohms as a random number because I don't know what I would want to use yet for the RF for the IF output yet, so I just kept that as that right now. I could probably change it and see how that changes my impedance for the RF input, so that maybe I need to change the matching network to my oscillator, to my mixer, to the input of the RF mixer. So you need to, so this basically what I'm going to be using is harmonic balance to solve for the input impedance here on this software called Usimmics that I have discovered, and it works pretty well, I guess. So I said that I was going to implement this into my software, but I thought it was pretty cool that I found this also, which could be very useful to design other circuits and to maybe even verify my answers too in my software too. So, but anyway, in order to find the input impedance to our RF input of the double balanced mixer here, we would use make sure that our diodes are compatible for a frequency that we would use for our RF input. Our RF input could be, for example, 2.4 gigahertz coming from the output of the low noise amplifier. And so we would need to make sure that our diodes could operate within that range, and it does operate within 3 gigahertz, so up to 3 gigahertz. So you would get all the parameters for the diode from my last video, which I used all these parameters. You would enter those into here. All the other parameters are default. Whatever you don't have, do not mess with it, other than just leave it what it's supposed to be, I guess. And then change the symbol to Shakti, since it is a Shakti diode. And that's it, 4 of them. And then use do not use 3 mutual inductors. it doesn't work for some reason. Maybe I did the simulation wrong that way when I did it the first time. I don't know, but I need to make sure I use. So the first time I used ChatGPT to help me with this problem that I had, because I thought it wasn't working when I was using 3 mutual inductors, so I had to use the 3 winding transformer instead, which it told me. I forgot exactly what the reason was, but we can say that we know our windings are 1-to-1 for the input for the oscillator, and then also for the input of the voltage, which will be the same. And that's it. So now, in order to find the input impedance to the RF input, we need to make sure that everything is connected. We have the local oscillator connected and our RF input connected. So we go to sources, AC voltage source, and change. So if we want an IF output of 100 megahertz and our RF input is 2.4 gigahertz, then our local oscillator should be 2.3 gigahertz. Connect those. And I can label this as LON, as local oscillator input. Alright, and now the next thing we need our RF input. So our RF input from our low noise amplifier could achieve a peak of, let's say, 0.001 volts, 1 millivolt for the peak. And our RF input would be 2.4 gigahertz. And then we need to also include a resistor of 50 ohms, because the output impedance of our low noise amplifier is 50 ohms. Connect them. So there you go. It's all connected. It could simulate, but the thing is that we need to find the input impedance to the mixer so that we can match our low noise amplifier to the inputs of our mixer here. So we would get a current probe. Put it there, and then we can call this RFN. Voltage. We also need our voltage, because we need to figure out what our oops, this is off. This should be connected to this part, because this is the low noise amplifier. We need to find the voltage. we need to find the input voltage to our mixer instead. So what we need to do is we need to make sure that that probe is there, and the probe is down here below the oscillator here. I mean below your basically it would kind of be like your low noise amplifier. So in order to find it, you would put those there. Or I wonder if I would have to put this to ground instead, but I'm not that sure. If anyone has a clue or an answer to this, that would be great. Maybe I should ground this instead of putting it here. But that's what I did. So we will show you what I get for the input impedance this way. So we can go to tabular here, and we need the voltage probe. So this is the voltage probe, DVB, and then this is the current probe. This one is not, that's actually the label. RFN is the label, so I don't know why, but it comes out with different numbers with that, and I don't know why that is either. But anyway, in order to find the input impedance from that, we can create an equation here, put the equation in here, call this ZRF. And the equation is RF in dot DVB, and then we would be using 2.4, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th row. So that's 10. And then divide that by RFN dot LB. Not L. I mean IB. There you go. Now you can simulate this again, and then get our answer for our ZRF and real imaginary components, and we get negative 23.1 plus J71.7 for our input of our to the input of the RF input of the mixer, double balanced mixer. Alright, if you see anything that might be off, please leave it in the comments. I would be very interested to know if there is anything that I'm missing here. But that's what I get for the input impedance to the RF input of the double balanced mixer. And I hope you liked the video, and please subscribe. Thank you. Bye.